All right, welcome to Solutions to AP Review number 2. We have two problems, one mostly involving forces, a little bit of kinematics, and friction plays a central role. In problem 1, we have a block that is struck and then slides up a ramp, comes back down. They want you to draw force diagrams so that you can use those force diagrams to understand how the time up compares to the time down. And kinematics can be used to help understand the connection between the two. So in terms of forces, make sure you don't draw components. Understand on a ramp that gravity is still going to be straight down. The components will become important later. Okay, so we have an mg and an mg, same one. We have a normal force, so even though that really doesn't come into play here, you need to draw it as part of your complete one, and make sure you draw it perpendicular. And then lastly, it's the friction. And you got to be careful. If the first one is moving up the ramp with a velocity v, then we should understand that friction is going to be opposing it. I'm just going to use a little f here. And then as it comes down the ramp, friction is going to oppose it. Okay, so there's our force diagram. Now they want us to understand what's going to be true of the time up versus the time down. Okay, the answer is the time down for this one is going to be greater than the time up. Okay, so t down is greater than t up. All right, that's one of the choices below. So we have to justify that. That's where 4 points is coming in. And you have to get this right to get other points there. So here's where we can use our force diagram. We want to basically relate time to acceleration. Okay, the easiest way to do that kinematically is use the equation x equals v naught t plus 1/2 at squared. And this is something that is subtle that come up like in both cases, up or down, at some point the speed is 0. Okay, so at the top right here, the speed is 0. So that's the final speed is 0. But I want to remind you of something, that this equation works just as well for final speed times time plus 1/2 at squared. They both work. So if the final speed for on the way up is 0 and the initial speed for on the way down is 0, then this is essentially 0. We don't have to worry about that. And that's really nice because then we can solve for time in terms of acceleration because distance is the same in both cases. So we can say that time is 2x over a. There's a square root there. But that really doesn't matter because what we understand is t and a are inversely proportional. In other words, if you can show that one has a bigger acceleration than the other, then you can show that the times are going to be different. So how do we go about showing acceleration? We'll look at forces. So in case A, okay, right, we have not only the force down, but we have the parallel component of gravity is down as well. I'm just going to put it right there. And in this case, the parallel component of gravity is still down. And we can see that since F and mg parallel are acting together, then they add. And so the sigma of the force in situation A, which I'll call up, is greater than the sum of the forces on the way down. Okay, because on the way down, the force as it's moving down, this is trying to accelerate it, but this is opposing it. So the consequence of that is that, according to the second law, that A up is greater than A down. And now we can apply that to this and say the bigger the acceleration up means less time, so we can say the time down is greater than the time up. If you didn't realize you could use this equation because of this part, then the alternative is you could use the simpler time is equal to distance divided by average speed. Okay, the average speed part's just a little trickier. All right, without spending too much time on it, I'll let you reason it out. But if we still have to take this approach in terms of forces acceleration. But if we know that the acceleration up is greater than the acceleration down, it stands to reason that the change in velocity has to be greater, and therefore we would have a greater average velocity up is greater than down. Okay, so if you have a greater acceleration, regardless of what direction we're moving, you're going to have a greater average speed. So a greater average speed up leads to less time up. That's a little trickier to reason out conceptually, but it works. Okay, so let's move on to I believe, the second problem. So this goes through this all. Take a look at it. That's 5 points. All right, so now we are pushing an object horizontally, and they want us to look at a few things. So again, a force diagram, and read it carefully. I can't emphasize enough because the key phrase there is constant speed. So you have to draw it didn't say just horizontal, so it's easy to forget. You got to draw the verticals. All right, we have an applied force F here, and then it's important that you not only draw friction and opposition, but you make it equal. Because of the constant speed, we know that the net force is 0. All right, so that's pretty straightforward. Now, next part, we say calculate the magnitude of the horizontal force in order to move it at 1.2 meter per second. And we have additional information. So we know coefficient, in other words. The idea is you should make some statement is that the force of friction equals F, or I really should do F is the force of friction because F net is 0. All right, so now that we do that, we can say F, which we already said is the force of friction, is mu times the normal force. There's a point for recognizing that. And then another point for recognizing normal force is equal to mg. Okay, so you plug in the numbers and you get a value. I'm not going to do that here. You can look that up. All right, moving on. Now things get a little bit more involved. All right, so part C. We at time 4, okay, the elevator opens and remains open for 5 seconds. So in other words, we have 5 seconds to get that box in the elevator before it closes. So you got to read that carefully to understand that. Calculate the magnitude of the new force the student exerts. Okay, so that might not seem obvious what we have to do right away. So I'm going to go to a blank sheet here. So in other words, we have our block. We have our door. I'm just going to draw it like that. Okay, and we've got essentially 5 seconds between wherever we are and to get to there. Okay, so 4 seconds has occurred already. So basically, we want to know a time. What do we know? Well, we got to know what distance we have to cover, and it would be nice to know what acceleration we're going to experience because we're increasing the force. So the most straightforward way we could do that, right, is we could say x equals v naught t plus 1/2 at squared. Okay? We want to use this equation to find the acceleration, because once we know the acceleration, then we can use that with the second law of motion to find what the new applied force F has to be. So this part is the most involved part here. So let me step back and let's do that again. So what we would have is while we are trying to gain speed to get to the elevator on time, we still have friction. We can say that our new F, that's what we're solving for, minus the force of friction equals ma. So our solution for F is simply equal to the force of friction, which we've already calculated, or you would have done earlier, plus ma. So we have to find the acceleration of this and then multiply it by a and then put it in there. So that's where this equation comes in. Okay, so what do we know? Well, we got to first figure out, actually I should extend this equation, plus x naught. In other words, at the time that we have of 5 seconds, that's a given. Okay, and we know v naught, we got to know where we are relative to the elevator. Okay, we're not at the original distance. So essentially, I'm going to solve this for a, right? So I'm going to have x minus x naught, put in parentheses, minus v naught t, all right, move that all over, multiply both sides, multiply that whole thing by 2, and then divide by t squared. Oops, that should be a squared. And that's my acceleration to get there. Okay, so your v naught is the original speed that it was moving from here to here. Time is the 5 seconds. All right, and the x minus x naught, you have to do a separate calculation based on the fact that this was moving with this v speed v for 4 seconds. So once you calculate that, then you can have this value here. You plug it in, you get your A. You plug your A in here, and you get your F. All right. Now, if this seems overwhelming, remember, you should be able to understand that the new force is based on the force diagram. Okay, and you apply the second law. And then that tells you, all right, I need to find acceleration. And then acceleration you know to find using kinematics. Even if you don't get this completely right, you miss a step. And by showing that information, you can get some partial credit. So don't panic if it comes to that. All right, so the last part is they want you to graph acceleration, velocity, and position as a function of time. All right, and there's two distinct parts, right? When we're moving at a constant speed for the first 4 seconds, and then when we accelerate. And if you understand that conceptually, it's pretty straightforward. So the first 4 seconds, we are moving at a constant speed, which means 0 acceleration. Constant speed is something up here, constant speed, some value, and then constant speed for position time graphs means a straight line. Okay. Then we picked up our acceleration. We started accelerating in forward direction, so don't have to worry about the transition. This went to some positive acceleration. This acceleration is a positive slope to the 9th second, and then from 4 to 9, this is a curve. I really shouldn't put a kink there. It should just be a continuation. I'm not sure how picky they'll be about that, but understand constant speed, straight line, accelerated motion, a curve.